Okay, in this video clip, what we want to do is explore the light clock in a more quantitative fashion. In the previous video clip, we did it in a qualitative fashion. Also bring out a few other points here that maybe got glossed over in the previous clip. So let's see what we've got here. I want to leave a lot of space here to do some work, so we have it way over here on the left side, but I think you can see that there, and we'll point out the salient details, of course. So Alice's clock. This is her clock as she sees it, the special light clock we talked about, the bottom mirror, the top mirror. One tick of her clock we'll call delta T sub A. Delta, as you may or may not know, Greek letter delta is often used as a symbol for a change in something or perhaps a lapse time. So that's why we're using it here. There's no special meaning to it or anything like that. It's just delta T sub A is one tick of her clock, which is the round-trip travel time for the light light pulse to get to the top and back down again. In fact, let's write an equation then for delta TA that we can do here. So we've got delta T sub A is going to be the travel time up and back down again. We know if we have a distance to cover and we have a certain velocity, if we're going 120 kilometers an hour, or if you want to do if we want to go 120 kilometers and we're going at 60 kilometers an hour, or if we want to go 120 miles, we're going at 60 miles per hour, we take the distance, divide by the velocity we're going, the speed we're going, and that gives us the elapsed time. So 120 kilometers at 60 kilometers an hour, 120 divided by 60 is 2 hours. Same thing for 120 miles and 60 miles per hour, 2 hours in either case. So delta TA then is going to be the round trip distance, and we're going to call this distance L from the bottom mirror to the top mirror. So it's just going to be 2 times L, L up and L back down again. L plus L is 2L divided by the speed of light c. That's how fast it's traveling up and then back down again. Okay, so that's an equation we're actually going to use a little later on here, but we have delta TA is 2L over c. Now let's look at Bob's perspective again. So here is the diagram, and just to bring out one thing that perhaps wasn't quite as clear in the qualitative analysis we did before, Bob, of course, is seeing Alice's clock moving here. So this is Alice's clock as Bob sees it. This is Alice's clock as Alice sees it, just sitting next to her. But Alice is moving now with respect to Bob at a velocity v. And so these are really 3 snapshots of Alice's clock as Bob sees it. So the first snapshot is when the light beam leaves the bottom mirror, and the upper mirror is up here. We didn't draw it in there. So that's one snapshot of Alice's clock. Here's the second snapshot right here, where the light beam hits the top mirror, and then the bottom mirror is down here in that position. And the third snapshot is back down again when the light beam hits the bottom mirror again, and the top mirror would still be right up here. So snapshot 1 of the clock, snapshot 2 of the clock, snapshot 3 of the clock. We just didn't draw in the top mirrors there, or actually the bottom mirror in the middle. We left that off as well. So it's just bottom mirror up to the top mirror and back down to the bottom mirror. This distance here is L, this vertical distance. It's going to be the same for both of them. You might ask, there's so much relatively weirdness going on here. How do we know L is the same? Maybe Bob sees L as something different. Alice's clock shrinks or expands or something like that. Well, there actually is an argument that we will consider later on to show that L will not change, that this vertical distance as Alice sees it will be the same for Bob as well. But we'll leave that to later time. We'll just have to take that as an article of faith at the moment. But what can we see here? Well, here's the path of the light beam. Bottom mirror up to the top mirror, back down again. That vertical distance L. We'll call this path length D. D up to the top, D back down. By symmetry, this length and this length are the same because it's a constant velocity motion as it goes along. And then finally, the bottom of this whole sort of triangle we've got here, we'll call it X. What is X? Well, think about this a minute. The round trip time is up and back down again. By definition, we're calling that delta TB. One tick of Alice's clock, according to Bob, is going to be delta T sub B. One tick of Alice's clock, according to Alice, is delta T sub A. And as we saw qualitatively, they're going to be different. We'd like to get a quantitative relationship between those two quantities. That's our goal here, to be able to say delta TB equals something something involving delta TA. So this distance here we'll call x. What is that? Well, that's just the total distance the Alice's clock travels from here to here to here. And that's just going to be the velocity of the clock, velocity of Alice and her clock going by, times the time elapsed. In other words, the time it takes for the light beam to go up and back down again, which by definition is delta T sub B. The tick time of Alice's clock for going back up and back down again as observed by Bob. So x here, this total distance x is just v times delta T sub B. So let's write now an equation. Let's block that off a minute. Let's write an equation for delta T sub B here. See what we can write down. We actually have a couple things we can do. Well, delta T sub B, by definition, the tick time for Alice's clock, as Bob observes it, is this travel time d, or actually not travel time, the distance d, plus another distance d. So the total distance covered is 2d divided by the velocity, which of course is c. Again, the principle of light constancy, as we talked about, Einstein's principle plus the principle of relativity, led him to the conclusion that the velocity of light, speed of light, was constant for all observers. No matter how they were looking at it, whether it's coming toward them or away from them or whatever, it always be measured at c, or some angle here like this, always measured at c. And this is the sort of root source of all the weirdness that, or most of the weirdness that you get in the special theory of relativity. So, velocity c up, velocity c down that way. The total distance is 2d, so the tick time that Bob sees is 2d over the velocity c. And right off that, you can say, well, hey, are we done? Because we have an equation for delta TA, we have an equation for delta TB. We can see right off the bat, because d is bigger than L, clearly. You know, here's L. The hypotenuse here of the little triangle is d. D is greater than L. Therefore, delta TB is greater than delta TA. The tick time that Bob observes is longer than the tick time that Alice observes. So Bob observes Alice's clock running slowly. In other words, that's the qualitative analysis we did before. And here we see it somewhat quantitatively, but we'd like something better. Again, we've got D here, we've got L here. We're not quite sure what those are. We'd like to have an expression involving delta TB and delta TA, and also maybe involving C and maybe V as well, but not L and D, because we could have different clocks, different lengths here, and so on and so forth, different velocities. So, what about another equation we can get out of here that maybe could help us? Well, if you remember your, not even really trigonometry, but probably algebra, early algebra, the Pythagorean theorem, right? Right triangles. And what we have here is a right triangle. We have L as one side. We have this distance here as the other side, and D is the hypotenuse there. So we know if we knew what this side here was, we'd have D squared equals L squared plus this side squared. Pythagorean theorem. So what's the question is, though, what is this side right here? Well, we said this distance here was x, which was the velocity of Alice and her clock, times the tick time as Bob observes it, the time to go from there to there. So that's good. And this is x over 2. So this divided by 2 essentially is this side. So let's just start writing that down here. Let's say, okay, Pythagorean theorem says that d squared equals L squared plus x over 2 squared. We'll just write that first. Okay? And now at this point, especially for those of you doing maybe a more quantitative approach, taking the more quantitative approach to the course, or even if you're just auditing, or the more qualitative approach as well, little challenge here for you would be to take what we've got so far. We've got this equation, and this equation. And we also know, we'll fill this in a minute, but we know x down here, what that is, involving v and delta TB. And can you put those together, manipulate them a little bit, and come out with a relationship just involving delta TB, delta TA, the velocity v, and the speed of light c? Because that's our goal here. So if you want to, pause the video clip at this point, spend a few minutes working with that, see how you can see how far you can get with that, and then come back, and which we'll do right now. We'll plow on here and persevere. So d squared equals L squared plus x over 2 squared. We can fill in some things here. We'd like to, remember, get rid of the d squared and the L squared, the d and the L here. And in a minute, we'll plug in this for x. But let's focus on d first here. From this equation here, if we rewrite this, pull the c over here, and divide each side by 2, we can see that d equals c delta tb over 2. That's good news, because now I can square that and plug it in here. We'll do that in just a minute. This one here, I can rewrite, and it tells me that L, multiplied by C here, L equals C delta TA over 2. That's good news, because I can square that and plug it in for L squared. And then the x there can be this. So let's plug all that in and see what we've got. So d here, if I square that, it's going to be c squared times delta tb squared. All over 2 squared is 4, of course, equals L squared. It's going to be c squared delta ta squared over 4. And I've got x squared over 4. Right? X squared, or 2 squared is 4. And x squared is v delta tb. So that's going to become plus v squared delta tb squared over 4. And now we're getting someplace. Because we say, I now have an equation, no more d's, no more l's, so those are out of the picture because we replaced them with equivalent expressions involving delta tb and delta ta. I've just got c's and v's in there, c squareds and v squared, so it's looking good. I have a delta tb squared over here, another delta tb squared over there, so in a minute we're going to try to combine those terms. Everything is divided by 4, so if I just multiply the whole thing by 4, I can get rid of the 4s, just cancel the 4s out. So these 4s will go away. And I'm just left with c squared delta tb squared equals c squared delta ta squared plus v squared delta tb squared. Let's bring all the delta tb squareds over on this side. So I'm going to take this term, subtract it from each side, bring it over here. So we'll write this as c squared delta tb squared minus that term, v squared delta tb squared equals c squared delta ta squared. Again, for some of you, if you've been doing a lot of things like this recently, you can almost do this in your head and jump ahead here. But we're going to take it step by step, try to make haste slowly here, not to go too fast, lose anybody. And again, pause it a minute, ponder things if you have to. I've got c squared delta tb squared, v squared delta tb squared. Let's factor out the delta tb squared there. So I've got delta tb squared times c squared minus v squared equals c squared delta ta squared. Just doing some algebraic manipulations here. And this is starting to look pretty good here. We don't need this anymore, right? So we'll just to get a little room here because I want to bring this up here and rewrite this here. So remember the goal was to write something like delta tb equals some other stuff involving delta ta. So let's divide both sides by this. We're going to bring this over here to the denominator. So we're going to write this as delta tb squared equals c squared times delta ta squared all over c squared minus v squared. Now we're really getting someplace. But we have a little bit more to do here. We've got some squares in there that we'd like to get rid of. And so I'm going to rewrite this just slightly, the right-hand side, as c squared over c squared minus v squared times delta ta squared. I really didn't do much of anything there. I just moved the delta ta squared out here. So we can focus on the c squared over c squared minus v squared. And now let's bring it back to the center of the board. So done all these manipulations here. We don't need this anymore either. We'll leave up our original delta TB there. And so let's bring it back to the center of the board so we can work with this. So we've got delta TB squared equals c squared over c squared minus v squared delta TA squared. Let's simplify this. We're going to use a little trick you may or probably may not remember. Something we talked about in the math review video clip, in the introductory set of video clips. We're going to rewrite this as, keep that c squared up there, as c squared times 1 minus v squared over c squared, and this still is delta TA squared, and of course delta TB squared over here. Okay? You should convince yourself that this is the same as that. C squared minus v squared is the same as c squared times 1 minus v squared over c squared. Multiply that by 1, we get the c squared. Multiply this times this. The c squareds cancel. I'm just left with v squared. So just a different way of writing this, and it looks actually like it's worse. And in general, it would be. But look what we've got here. Now we can cancel these c squareds. I've got a c squared in the numerator, a c squared in the denominator. Get rid of that. Get rid of that. And so we can write this as delta TB squared equals 1. So we have a 1 now here on top over 1 minus v squared over c squared times delta TA squared. But now let's take the square root. Get rid of these squares. Since all our quantities are positive, you may remember when we do square roots, we've got to do a plus minus thing to be precise about it. In this case, everything's going to be positive. So we can write delta TB. What we're doing is we're just taking the square root of each side. Square root of this is delta TB equals the square root of this. 1 minus v squared over c squared times this whole thing times delta TA. And one more thing here, just to simplify slightly more. Again, we'll want to bring this up in the center so we can look at it. So hopefully we've got all that done. Let's just bring it up here. So, and rewrite it just slightly more, because you may remember if I've got the square root of a fraction, numerator, denominator, that's the same as the square root of the numerator divided by the square root of the denominator, but the square root of 1 is just 1. Again, everything being positive here. So we can rewrite this as delta TB equals 1 over square root of 1 minus v squared over c squared times delta TA. And that is our final result for our quantitative analysis of the light clock. It's going to be a very important result as well. Let's just analyze a little bit, make sure that things check out as much as possible. So here's our final result. First of all, we said that delta TB was greater than delta TA. We argued it qualitatively. We saw it sort of semi-quantitatively here. We knew that D was bigger than L, and therefore delta TB must be a bigger number than delta TA. Again, the idea is that the moving clock ticks more slowly from Bob's perspective. Does this result here also indicate that? Is delta TB greater than delta TA? If it isn't, after all that manipulation, then probably we made a mistake someplace along the way, or our earlier analysis is incorrect. So let's just think about this a minute. And let's also think about a couple extreme cases here. What happens if V is 0? Okay, if V is 0, that means Alice's clock isn't moving at all. It's just like Alice and Bob are side by side, and they're sitting there, and they've got their clocks next to them, and they should be running the same if they're identical clocks. If V is 0 here, this becomes 0, so I've got 1 minus 0. Square root of 1 is 1. I get 1 divided by 1 is just 1. I get delta TB equals delta TA, as we would expect. In other words, if they're just sitting there next to each other, there's no difference in their tick rates, assuming that they are identical clocks. And the math is checking out for us there. So that's okay. What happens if v, let's think about another extreme case, what happens if v equals c, if Alice is actually going at the speed of light? Well, if v equals c here, I've got c squared over c squared then. That's 1. 1 minus 1 is 0. I've got a 1 divided by 0 situation. This is infinite. Okay? So that's a problem. But it's an indication from the mathematics that Alice's velocity can never be equal to the speed of light. In fact, we'll do more arguments later on this, essentially that nothing can travel at the speed of light because you get these contradictory situations that delta TB equals infinite times delta TA. Okay? So rule that situation out. What about everything else with velocity between 0 up to but not quite the speed of light? Any of those situations? Well, v then is going to be less than c for sure. So this quantity right here, v squared over c squared, is going to be the square of a fraction, which gives you another fractional number, something like 0.8 or 0.792 or something like that. So I'm going to have 1, essentially, this, to say it another way, this number is going to be between 0 and 1. If you're not sure about that, get out your calculator, just do some examples here with v and c, and you'll see you always get a number that's like, again, 0.8, 0.32, or whatever. So I've got 1 minus a number between 0 and 1. That means this whole thing inside here is going to be between 0 and 1, a positive number. The square root of a number between 0 and 1 is always between 0 and 1. So I'm going to have 1 divided by a number that's between 0 and 1. Another is a number smaller than 1. I'll give you an example. I might have something like this. It'll be 1 divided by perhaps, just say 0.8. Maybe the square root of this thing in here comes out to be 0.8, between 0 and 1. Well, 1 divided by a fraction like that, this is 0.8 or 8/10. That's 10/8, a number bigger than 1. So our little analysis here essentially says this quantity right here is always going to be greater than 1. Could be equal to 1, actually. It's going to be greater than or equal to 1. It's equal to 1 if v equals 0. But if v has any magnitude at all, it's going to be greater than 1, and therefore I'm going to have a number greater than 1 times delta TA. That means delta TB is going to be greater than delta TA. And this special quantity here, this 1 over the square root of 1 minus v squared over c squared, occurs a lot in the special theory of relativity, and therefore it's given a special name. We say it equals the Greek letter gamma, a special symbol for it. And one of our next tasks will be to explore gamma a little bit, and especially in terms of time dilation, and then a little bit later on in something called length contraction as well. But we want to get a feel for gamma and this v squared over c squared business here to see when this really matters, when time dilation actually occurs, so that we could see it perhaps in the real world. But remember that the basic idea here is that this is, I just mentioned it, we call this time dilation. Time dilation. Another way to say that is moving clocks run slow. They tick more slowly than if they're not moving. So again, if Alice and Bob are right next to each other with identical clocks, they both look at them and say, just fine. When Alice goes in motion, however, at some velocity v, passing by Bob with her light clock, as far as she's concerned, her clock right there is just ticking away nicely. Nothing weird about it. Bob, however, sees her light clock acting like this, where it goes up and comes down again at a diagonal, and therefore he sees her clock ticking more slowly. He tells Alice, hey, Alice, something's wrong with your clock because it's not working like it was before. I've got my clock right next to me. It's ticking away just fine. Your clock is now ticking more slowly. Each tick takes longer time than it did before when I compare it to my clock. So that's the whole idea of time dilation. And really, you can reverse the process. You could say Alice, looking at Bob's clock, is going to get the same result. And also, she's going to see his clock ticking more slowly. And so you might be thinking, well, what's the deal with that? How do we understand that? So we'll have to figure that out. Although really, it all comes back down to the relativity of simultaneity. The idea being, again, a rough analogy might be if you're looking at somebody off in the distance and they look small to you, and yet you know their regular height if they're right next to you, and they looking at you, you'll be looking small to them. And we think nothing of that because it's just part of our everyday experience. This type of time dilation is not part of our everyday experience because for it to really become a factor, velocity has to be very high up near the speed of light. And typically we don't deal with things like that, so we don't see it. If the velocity here is very low compared to the speed of light, this is a very, very small number. This square root then is pretty much the square root of 1, and it's just 1 divided by the square root of 1, maybe just slightly different, but the difference is so slight for all practical purposes as we observe things, delta TB equals delta TA, and we don't observe that effect. But when you get the speeds up closer to the speed of light, then this time dilation business comes into play. And so we'll want to explore that a little bit more as we proceed.